I think it's time. Can everyone hear me? Yep. Great. So thanks for having me on this virtual science forum. I'm Julien Barrier. I'm a PhD candidate at the University of Manchester in the UK. And now this talk is about our recent research on Brown-Zak fermions, namely the family of quasiparticles that are created in periodic potentials exposed to high magnetic fields. I'll first start with the general structure of the Hofstadter spectrum, that is the non-interacting model in our graphene superlattices, and then I'll tell you a bit more about ballistic motions of Brown-Zak fermions and their properties at low temperature. So before I start, let me thank the people who contributed to this work, the Spiren who made the main device that we present, and we've been discussing these results with Alexei, Volodya, and Andrei. I'd like to note that Roshan was the first to have the intuition of this ballistic motion, and we published these results very recently last week in Nature Communications. And I think if you're more interested, you can have the link of the archive that has been updated recently. That is on the Visual Science Forum website. So let's start first with the periodic potential and no magnetic field in a system. The Bloch theorem tells you that the periodicity of the wave function would be the periodicity of the lattice, and therefore all the electrons would propagate without actually seeing the lattice. The important length scale in this system is the lattice constant A. There's something important here, that if you consider the periodicity, you have an energy diagram that is no longer continuous. It has gaps, and you can fold this into a so-called Barrier zone that takes into account the periodicity. And usually you have an integer number of electrons per unit cell. So if you place the Fermi level between the bands in the gap, you can define a band filling factor S that is basically the derivative of the electron density within the unit cell and normalized with the unit cell volume. I forgot this A0 square, sorry for that. So that it's a dimensionless quantity, and this, interestingly, S is an integer. This integer corresponds physically to the number of band gaps that are filled because of this periody boundary condition. On the other side, if you consider a 2D electron gas exposed to a magnetic field, now you have a Lorentz force that drives the electron into cyclotron motions. What's interesting here is that each orbit contains one flux quanta, or an integer number of flux quanta. And of course, orbits are quantized, and this is the description of what Landau levels are. And in this system, the electrons do not contribute anymore to the propagation of the current. The relevant length scale in this system is the magnetic length, LB, that is like 1/√of B. It's 25 nanometers at 1 Tesla. So you imagine that for a normal lattice with a lattice constant in the angstrom scale, you would have 10,000 Tesla for these two to be commensurate. But this is nonetheless an interesting question: what happens? And this has been first noticed by Asbel theoretically. He's shown that this quantum mechanical problem, when A and LB starts to be commensurate, is exactly solvable when the ratio between the magnetic flux and the area of the unit cell is a rational number P/Q. This solution of this problem has Q eigenvalues, and the states for which the flux is a rational P/Q of the flux quantum, we describe this with an associated family of quasiparticles that are the Brown-Zak fermions that we study. I think it's interesting to note that what is a continuous variable, like the magnetic field, would have a discontinuous single particle energy spectrum for every fraction P/Q. Let's now study how electrons would behave in such a superlattice at high magnetic field. That's what Douglas Hofstadter computed in the 70s. He plotted the eigenvalues for this problem. And in between the eigenvalues, you can see the black regions are the gaps for the problem. And the gaps on this system are continuous. I think it's interesting to note that each band is composed of minibands that is composed of minibands, so you have this fractal structure. And at the bottom of this diagram, you see what would be the integer quantum Hall effect that happens in Landau levels, that is the limit of small magnetic fields. And that makes sense if you consider that in a normal crystal, the Hofstadter butterfly is not accessible, or at least would be accessible in 10,000 of Tesla. So now there's a different way to plot this, which is the Barrier diagram. So Barrier realized that you get a better physical picture when you change the electron density instead of the energy, and you plot this versus the magnetic flux, the normalized magnetic flux. So I reversed this. This was previously plotted energy in X and the flux in Y. I reverted this so that it's clearer in this picture. So if you follow the first gap, that would be this blue line in the Hofstadter butterfly, and the first gap would result in this, with these quantities in a straight line as well. If you look at the gap at -1, you would have again a straight line. That doesn't change that much, but it becomes interesting when you take the second gap for nu equals 2, that this zigzag line would translate in the Barrier diagram into a second line with a slope that is twice the slope of the first one. You can do this for nu equals 3, nu equals 4. This translates into this line, and because everything is symmetric in this problem, you can draw all these lines, and that is what is described as the Barrier diagram. Now you notice that at fractions, 1/2, 1/3, 1/4, 1/5, etc., you have this line that the gap follow, and this appears to be vertical lines at constant flux, 1/2, 1/3, and 1/5, and that's those states that we describe as magnetic Bloch state or Brown-Zak oscillations in different experimental works. All these functions would be described by this S and T integer. So S is the intersect, T is the slope. They're both integers. S is described as we shown by the McDonald equation, and is the number of field bands that you have in your system. So it turns out that for graphene only, you cannot really assess the Hofstadter butterfly, but if you combine it with the hexagonal-boron-nitride that is 1% larger than graphene, for which the lattice is 1% larger, you combine them, you stack them and align them, and you have a moire superlattice that appears. And it turns out that the lattice structure, the lattice constant for this moire superlattice is about 14 nanometers. So the flux 1 for this system would be accessible around 30 Tesla, which is something that we can do in our transport experiment. The stacking has been done with great success. Here are a few STM images of graphene on top of hexagonal boron-nitride and the 2 layers aligned. And if you measure what this gives you, this is a plot of the electron density using spectroscopy, and you have here the Dirac point, and if you go to larger larger voltages, you have another anomalies that start to appear. And these are anomalies because if you think about the moire superlattice as a modulation or a perturbation of the periodic lattice, you would form another Bloch band, considering this is a larger unit cell, and you would fold back this new band into the superlattice Brunner zone that is smaller because of the unit cell is larger, and at the end there's a gap that opens up. So you have the main Dirac point here, you raise into energy main Dirac point, and you see these anomalies that correspond to this superlattice Dirac points here. And that is very similar to what can be done in transport. So to compare, I've plotted the Landau fan for monolayer graphene with misaligned HBN. And we see the conductivity sigma x acts as a function of the backgate voltage and the magnetic field, and it goes from black to yellow in this picture. The main features here are the black lines that indicates the energy gap in the Barrier diagram. And they all trace back to zero density, zero magnetic field, and that is the properties of Landau levels. At higher field, you can lift the degeneracy, that would be the fractional quantum Hall effect, but we don't observe that here. And interestingly, the conductivity is very high at zero and decreases drastically upon increasing the magnetic field. Now, if we put the superlattice potential, we have a much richer diagram. Not all the lines go back to 0, 0, and we're right into the regime of the Hofstadter theory. And here, bright regions at higher fields start to appear. I'll show later that they correspond to these high mobility Brown-Zak fermions. Now let's describe this in terms of Barrier diagram. This is a zoom in over the electron doped region at high magnetic field on a graphene-on-boron-nitride devices. What's interesting is that T here simply describe the quantum Hall conductivity. This has been shown by Thales in the 1980s. And in this quantum Hall phases, S will describe the number of electrons that you get into one superlattice unit cell. And with all of that, we can classify everything as we can classify all these states depending on what S and T are. So if you get 0, S, and T integer, you've got the integer quantum Hall effect. If you get S equals 0 and T fractional, you get the fractional quantum Hall effect, and you are right into the regime of Hofstadter Barrier when you get integer for S and T. So that's the basic of the measurement we have. Now I'd like to talk about the Brown-Zak oscillations that were introduced by Roshan Krishnakumar a few years ago. These are conductivity oscillations that appear each time you get into the commensurability condition, where the flux is a unit fraction of the flux quantum. And what we have in this regime is a peak of the conductance that can be measured. Interestingly, in this condition, electrons propagate through the plane as if the magnetic field is absent, but with a dispersion that is determined by the new miniband spectrum. He later reported additional fractional states with, again, slightly higher conductivity. So here we're right into the regime where the magnetic length is commensurate with multiples of the lattice constant. Now that we have all this background, let's go to what we actually did in this work. So we have a large graphene HBN devices that is 7 micron wide. We made this with the dry transfer technique with the top graphene aligned, top HBN aligned to graphene, sorry, and we had a second HBN layer for encapsulation, and this is intentionally misaligned to dodge any competing Moiré patterns. At zero magnetic field, we observe a mobility that is very high, on the order of 10 to the 5th, 10 to the 6th centimeter square per volt per second. And it's still somehow limited by edge scattering because of the finite width. And we can see this by showing the mean free path of the electrons in this device, and it's still limited around 17 microns. We made also transverse magnetic focusing using small magnetic fields, and that is consistent with the high mobility we are able to measure in these devices. So these devices do propagate the current in a ballistic manner, and that's what is shown here. So we based this kind of measurement on Binecker and Van Houten that throw a current from 1 to 2 and measure from 3 to 4. So if you have a diffusive transport, then charge carriers would get predominantly where the current is flowing, so from 1 to 2, and you wouldn't measure anything in particular from 3 to 4. But if you have a ballistic device, what what you measure is actually that the electron would shoot straight across the device and would go from 1 to 3, hence having a charge accumulation on contact 3, and depletion, that is this negative resistance that you're able to observe right here. This has been shown already in other graphene devices on the same geometry. And because we have hole bars, we try to adapt this geometry. So if you get the current from this contact 3 to 7, and you measure the band resistance from 1 to 2, then you would see the negative resistance if the device is ballistic. And when you have ohmic contribution, the resistance would go back into positive. And that's exactly what is shown here. You have a negative band resistance at 0 field, and the resistance increases and goes back into positive as soon as you apply a magnetic field. So this device is ballistic, and that's very interesting for what follows. So now this is a conductance map for which we've got the formula sigma xx here. And this is measured on this 17 microns wide a device with varying gate voltage and magnetic field. It's been measured around 10 to 30 millikelvin, and I'd like to focus your attention on the level of detail that we're able to achieve here. This is much better than what you'd previously done in transport experiments. So the first thing we can observe here are the bright horizontal lines. Yellow, which corresponds to high conductivity, and they are marked for fraction of the flux quantum. So you have 1 at 1/2, 1 at 1/3, 1 at 1/4, etc., etc. These are the Brown-Zak oscillations that I've introduced just earlier. And these yellow streaks correspond to the recovery of the translational symmetry, that is P flux quantum penetrate through Q superlattice unit cell. And they show the emergence of Bloch states that experience 0 effective magnetic field. And along each of these horizontal streaks, you can find numerous neutrality points that appear and Van Hove singularities. They reflect the differentialization of Brown-Zak fermions for different staggered fluxes. And we can see this Landau mini-fans that appear. They radiate from this neutrality point in both directions along the magnetic field axis, and they represent the Landau quantization of the Brown-Zak fermions around non-zero effective fields, at non-zero effective fields, sorry. Here I show an example of what the mobility is for these Brown-Zak fermions. So this is the mobility at flux 1/2, around 15 Tesla here. And it's in the order of a million at 15 Tesla, which is highly unexpected. Another quantity of interest that we have is the mean free path. To extract it for a measurement, we use the Drude model and assume an isotropic spectrum. For the states at 0 field, the mean free path would be calculated from the formula here, with L being the mean free path. G is the degeneracy of the states that changes from the degeneracy of the Dirac fermions at 0 field. E is the electron charge, H is the Planck constant, K of the Fermi wave vector, and L what I'm calculating. So G is defined with G spin and G valley, but we add an additional quantum number, Q, for the Brown-Zak fermions, which is the denominator of the fraction P over Q. And I will show experimentally later why we do add this Q factor. So now that we calculate the mean free path with the following formula, you find a mean free path that is very high and is still limited by the device width.
Sorry, how does especially the first number, mobility, compare to the pristine device with no superlattice?
So the mobility was in the order of several millions. a few millions, and the mobility is still in the order of several millions at 1.5.
So you're basically saying it's nearly the same as without magnetic field with very okay.
Yeah, the thing is, because of the recovery of the translational symmetry in these states, the Brown-Zak fermions do experience no effective magnetic field in this region. So to verify this, we did a transport in the band resistance geometry to see if this was negative, and what happens in this device is that we have region in green where the resistance is negative. That is detailed on this side. Interestingly, only the fractions 1/q do have a negative band resistance. But we still have this ballistic motion that is confirmed with this geometry. So now I'll focus on this region on the map to show the consequence of this very high mobility for the Brown-Zak fermions. So the high mobility results in the quantization, the Landau quantization in small effective fields, and this is the thing that allows us to find experimentally the degeneracy for different P and Qs. So this is the high resolution map between 1/2 and 1/4 for positive gate voltages, which is positive carrier n/n0 densities. So you see this Landau levels that originate from the main Dirac point that are plotted as white lines on this diagram. And you can plot the magnetic Bloch states, so Brown-Zak oscillations at fractions 1/3, 1/2 is a bit higher, 1/4 is this line on the axis, and additional fractions, 2/7, 2/5, etc., etc. So every time a fraction of the flux finite. And with that, you can identify the Hofstadter gaps that are the Brown-Zak fermions Landau levels for different P/Q. For example, for P equals 1, you can have Q equals 2, and this many fans that appear that are grown there, Q equals 3 and Q equals 4. Interestingly, we have other occurrences of that. So for P equals 2, you have Q equals 5 and Q equals 7. And all the time this many fans. And this repeats for different generations of Brown-Zak fermions. Interestingly, the spacing between these Landau levels matches Q. So for example, at 1/3, you would have a spacing that is 3. So 6, 9, 12, 15, 18, etc. And that is repeated for every occurrence. At 2/5, for example, the Landau levels would follow the sequence 4, 9, 14, etc., which is a separation of 5 in between these states. And this is always true. So independently of P and Q, we observe a Q-fold degeneracy. But that is by taking into account that both the spin and valley degeneracy are lifted by exchange interaction. So the total degeneracy for these states is 4Q. And we define this Q, which is the denominator, as a new quantum number that describe these Brown-Zak fermions. There's, however, one exception.
Sorry, can I ask a question related to this slide? Could you please repeat the physical meaning of why is there additional degeneracy just in one sentence?
So the separation between all these states, these Landau levels, you would have a gap at nu equals 6, nu equals 9, nu equals 12. And this is the separation delta nu between these gaps is equals to Q instead of 1 or 4. So this is an additional number that describes the degeneracy of these states. So the degeneracy would be the spin degeneracy multiplied by the valley degeneracy multiplied by Q.
Oh, okay.
Show, as you can see here.
Okay, thank you.
You're welcome. So interestingly, we have an anomalies around 1/3. If we measure at low temperature with a low, relatively low current, we have additional gaps in the diagram that are not predicted in the single particle Hofstadter model. And they disappear very quickly. So if we stay at the same temperature and increase a little bit the input current, we see these states disappear and only remain the Q-fold degeneracy. So 7, 8, 9, 10, 11, etc. disappears at high temperature. So these are minima that are quite fragile, and they do not exist, as I said, in the single particle model. And they correspond to the lifted mini-valley degeneracy. And the fact that we can lift the mini-valley degeneracy for these states justifies in itself the framework of a new fermion model to describe this high magnetic field states. So finally, we notice something else interesting on the diagram. So if you look on the whole side, on this part, sorry, if you look on this region, you would see that you have an expected bending of the Barrier diagram. So if you look around here in details, the Landau level seems to not follow straight line trajectories. It was predicted by Barrier and Hofstadter, and bend toward the n-axis. So this was not explained by any theoretical model, and electron interaction would play a significant role here for lifting the degeneracy, for example, at low temperature, as I've just shown. So it would be reasonable to expect that these interactions are also involved in these anomalies. But we don't really understand because it's the gate capacities of the states remains constant. So it should not have that much of influence in bending this. So I think further research would be necessary to decipher this unusual behavior. We have a bending and a Stakers-like features in this state. So to summarize this, what we observed in this work was that Brown-Zak fermions are a new family of quasiparticles that are defined in graphene superlattices, but more generally in any moire superlattice exposed to high magnetic fields. Whenever the magnetic flux is commensurate with the size of the superlattice, the magnetic length, sorry, is commensurate with the size of the superlattice, you have a high conductivity here. So the high mobility of the states allows a complete resolution of the Brown-Zak minifans, together with a lifting of the superlattice-induced mini-valley degeneracy. And I think this work shows that the magnetic field can be treated on equal footing with other parameters of van der Waals central structure, like the constituent material, the lattice structure, the number of layers in the alignment, because it allows the creation of new metallic states, high quality electron states, and I think looking at these states and trying to decipher what they show would be an interesting direction for further research. So thank you very much for your attention. Any question?
I have a question actually. So if you say if you look at the single family of Brown-Zak fermions, so let's say we landed on a commensurate flux per unit cell. how does the band structure look like? For example, is it does it inherit the crystal symmetries or not, or is it something anisotropic?
We assume, so I don't really know what the band structure looks like, but in the calculation to calculate the mean free path, for example, we assumed an isotropic spectrum of the Brown-Zak fermions. It's quite complicated because the band structure for every Brown-Zak fermion would be different.
Sure.
As they're different, so it would necessitate further calculations.
But this wasn't done yet, or was it?
I'm not sure. I think it has been done. The group of Volodya Falco at Manchester has shown several papers about it, but I'm not sure whether they do provide a formula for every occurrence of this states.
Mm-hmm. No, so just to understand also, to explain also a little bit the reason for my question. This is a non-magnetic band structure because, sorry, it's a conventional band structure with no flat bands, so it's dispersive. But at the same time, it has no reason to be symmetric under time reversal. So in principle, you could observe, if it was asymmetric spatially, you could observe fun phenomena like non-reciprocal response and such, like current this way, not equal current that way, etc. Do you know of anything like that?
I'm not sure this has been done yet. We haven't done it. Just want to say that some of these Brown-Zak fermions would have a flat band. Not every one of them, or something relatively flat, not always as flat, but it can be very, very, very parallel on some occasions. It just needs some theoretical calculations to look at what happens on every case. Unfortunately, I haven't a slide showing that, but this paper, sorry. One of these two papers details the band structure. I think this is the PNAS one that shows some calculations of the band structure in these states for the higher order fractions. Yeah.
All right, thanks.
You're welcome. Any other question?
I mean, if nobody asks, can I ask about experimental setup where you showed something like two contact system and then the sheet in between consisting of graphene with boron nitride on top of it, and there were gates under it, like a lot.
Oh, okay. So we use this sort of device. So yeah. It's so it's a sandwich of graphene in between two hexagonal boron nitride. The top boron nitride is aligned with the graphene layer, and we have gold contacts that are deposited here.
Mm-hmm. So do you? So I was just wondering about the connection between those contacts and graphene and boron nitride. Is it not destroying the structure of graphene and boron nitride, making those contacts? Just how
No, we use these are point contacts, so they interfere. So no, they don't destroy the actual structure when we deposit the contact.
So but do you put it on top, or how?
Oh no, they are on the side. So you have this three layers, and then you have the contact that goes on this side.
Okay, and there is no like anything in between or something?
Sorry, there's no?
There is no anything in between. It's like exactly pure contact between gold and graphene and boron nitride, right?
We hope that. In practice, it's hard to tell.
Okay. And what is the age of this boron nitride or graphene? What's the shape of it? There is like this armchair, zigzag and stuff.
We etch the device, as you can see here. So the edge is quite random.
Okay. No, I was just wondering about those contacts related to my own problem. So it's I'm not really nitpicking to your experiment. Yeah, thank you.
I actually have another question. So it seems like you have essentially no rotation or no disorder in the lattice constant, whereas I think if you compare with the twisted bilayer literature, there it's assumed to be the dominant source of disorder. Do you have any comment on why such a difference? So both are, of course, sticking to flat materials together, and the fabrication is essentially the same, or at least from yeah.
That's something with boron nitride, is that if you align them, the lattice constant is slightly larger than the one of graphene, and the boron nitride would expand or shrink a little bit to adjust to that graphene structure. And then randomly you would have what are called bubbles, which are hydrocarbons, impurities located within the two layers of graphene and HBN. But we choose a layer that has the least possible number of hydrocarbons bubbles. So the least number of impurities in these devices. I think the reorganization of boron nitride on top of graphene is responsible for this.
All right, thanks.
Any other question? If no, thank you very much for your attention. I encourage you, if you have any question, to look at the archive paper. And thank you very much.
Thanks for the talk.
Thank you.
Thank you.